This is a question from Gate 2016 from Chemical Engineering, question number 49. A porous pellet with platinum dispersed in it is used to carry out a catalytic reaction. Following two scenarios are possible. Scenario 1, platinum present throughout the pores of the pellet is used for catalyzing the reaction. Scenario 2, platinum present only in the immediate vicinity of the external surface of the pellet is used for catalyzing the reaction. At a large value of Thiele modulus, which one of the following statements is true? A. Since the reaction rate is much greater than the diffusion rate, scenario 1 occurs. B. Since the reaction rate is much greater than the diffusion rate, scenario 2 occurs. C. Since the reaction rate is much lower than the diffusion rate, scenario 1 occurs. And D. Since the reaction rate is much lower than the diffusion rate, scenario 2 occurs. So this is a question from Chemical Reaction Engineering 2 from catalysis part, and the reference NPTEL series can be found in lecture 9, Introduction to Intraparticle Diffusion, Chemical Reaction Engineering 2 by Professor Sanjay M. Mahajani, Professor Ganesh A. Vishwanathan and Professor A.K. Suresh from Department of Chemical Engineering, IIT Bombay. So here there are two scenarios given here. So let's say this is our pore or active site on the catalyst. So you have a particle. So the first two steps in catalysis is that this particle from the bulk has to first diffuse externally to reach the external surface of the catalyst. So this is called as external diffusion. Then your particle has to diffuse into the pore or the active site of your catalyst, and that is called as internal diffusion. And then your particle has to get adsorbed, then react and desorb after forming the products. So these are the various steps that are happening in a catalytic reaction. So here one data that they have given is that the value of the Thiele modulus is very large. So by this we can say, Thiele modulus is defined as the ratio or the root of ratio of the surface reaction rate by internal diffusion rate. So if Thiele modulus is very large, that means your internal diffusion rate is very low. Or in other words, this system is basically controlled by internal diffusion rate, or internal diffusion is rate controlling. Right. So here your particle externally diffuses to the surface. So let's say you have multiple particles. These particles will first diffuse to the external surface, and then from here they have to diffuse internally to the catalyst activation site. And this step, this internal diffusion, is very slow. But after diffusing when the reaction happens, that is a very, very fast step. Okay, so what happens basically is, so your particles are right now, let's say, on the external surface, and let's say one by one they are diffusing into the internal surface very slowly. The moment they get adsorbed on the catalyst side, reaction happens because the reaction rate is very fast. So the moment this your reactant particle gets adsorbed on the active site of your catalyst, reaction will happen very fast, and because of this, this particle will basically just vanish immediately. So when an observer looks from the outside, they won't see this particle here. Rather, they'll be looking at the particles which are on the external surface of the catalyst. So that means when an observer looks, there will be only particles on the external surface. There will be nothing inside the active site, because whatever is getting adsorbed into the active site is reacting very fast because the reaction rate is very high. So this is basically equivalent to your scenario 2, where the platinum or the particle which is platinum here is present only in the immediate vicinity. This immediate vicinity is basically the catalyst surface just outside the active site. So the platinum is present only in the immediate vicinity of the external surface of the pellet used for the catalyzing the reaction. So scenario 2 will happen here because of the large value of the Thiele modulus. And because the Thiele modulus is very large, your internal diffusion is rate limiting. So that means your reaction rate is much greater than the internal diffusion rate. So putting together everything, option B will be the right choice here, because as the Thiele modulus is very high, your reaction rate is much greater than the diffusion rate, and because of the explanation that I just mentioned, the platinum will be found only in the immediate vicinity of the external surface of the pellet. So your right option here is option B. Since the reaction rate is much greater than the diffusion rate, scenario 2 occurs. So Riaz, you are like partially right. Like the reaction rate is much greater than diffusion. That is also in option A. But then the problem is, what is the fate of the platinum? So will the platinum be found in the through the pores of the pellet, or will the platinum be found only on the external surface of the pellet? And because I hope this explanation was understandable, because of the fact that your whatever is getting adsorbed inside the pore reacts immediately, from an observer, from an outside point of view, there will be only platinum present on the immediate vicinity or the external surface of the pellet. So that is why option A is not the right answer. Instead, option B is the right answer. Was it clear, Riaz? Okay, fine. We'll solve one more question. Okay. This is a question from GATE 2015 from Chemical Engineering, question number 57. A catalyst slab of half thickness L, the width and length of the slab are very, very greater than L. is used to conduct the first order reaction A giving B. At 450 Kelvin, the Thiele modulus of the system is 0.5. The activation energy for the first order rate constant is 100 kJ per mole. The effective diffusivity of the reactant in the slab can be assumed to be independent of the temperature, and external mass transfer resistance can be neglected. If the temperature of the reaction is increased to 470 Kelvin, then the effectiveness factor at 470 Kelvin up to 2 decimal places will be dash. The value of universal gas constant is equal to 8.314 joule per mole per Kelvin. So this is a question based on internal diffusion from Chemical Reaction Engineering 2, and the reference NPTEL lecture can be found in lecture 10, Intra-particle diffusion, Thiele modulus and effectiveness factor part 1, Chemical Reaction Engineering 2 by Professor Sanjay M. Mahajani, Professor Ganesh A. Vishwanathan and Professor A. K. Suresh from Department of Chemical Engineering, IIT Bombay. So, in this question, our main objective is to find the internal effectiveness factor, which you can represent as eta at 470 Kelvin. And this internal effectiveness factor can be found by using the formula tan H phi by phi. And this phi is basically the Thiele modulus, which is equal to L into root of K by dE. And since the effectiveness factor needs to be found at 470 Kelvin, you need to find the Thiele modulus at 470 Kelvin. Or in other words, this K, reaction rate constant K, is also at 470 Kelvin. So let us write down the data they have given us in this question. So the first data they have given that Thiele modulus is equal to 0.5. Let's say this is Thiele modulus for case 1. So Thiele modulus phi 1 is equal to 0.5. Other data they have given is that the activation energy EA is equal to 100 kilojoule per mole. And they have also mentioned that the effective diffusivity of the reactant in the slab can be assumed to be independent of the temperature, and external mass transfer resistance can be neglected as well. So based on all these data, let us see how we can find the internal effectiveness factor at 470 Kelvin. So let us first start by using our Arrhenius equation. So by Arrhenius equation, ln K2 by K1 is equal to E by R into 1 by T1 minus 1 by T2. So here EA is given as 100 kilojoule per mole. This is basically 100 into 10 raised to 3 joule per mole. Then T1 is basically 450 Kelvin and T2 is 470 Kelvin. And the universal gas constant R is also given as 8.314 joule per mole per Kelvin. So just substituting these values in the Arrhenius equation, we can get ln K2 by K1 is equal to EA, that is 100 into 10 raised to 3 by R 8.314 into 1 by T1 minus 1 by T2, that is 1 by 450 Kelvin minus 1 by 470 Kelvin. So solving this, we can solving this and taking the exponential, we can get K2 by K1 is equal to 3.118. So let us take this as equation 1. Now for our next step, we need to use the concept of Thiele modulus. And Thiele modulus 5 is given as L into root of K by dE, where dE is the diffusivity or mass diffusivity, K is your reaction rate constant, and L is the catalyst slab length. So phi 1 will be L1 root of K1 by dE1, and this phi 1 is the case 1 at 450 Kelvin, and phi 2 will be L2 root of K2 by dE2, and this will be for 470 Kelvin. So in the question, they have given that phi 1 at 450 Kelvin is 0.5. So using these, we need to find phi 2 at 470 Kelvin. Now, other data that they have given is that L is constant because the length does not change with temperature. So L1 is equal to L2. Also, they have given that your mass diffusivity is independent of temperature. That means dE1 is equal to dE2. So if we write phi 1 by phi 2, on the right hand side we will get L1 root of K1 by dE1 by L2 root of K2 by dE2. So because L1 is equal to L2, we can cancel out L1 and L2. dE1 is equal to dE2 because the mass diffusivity is independent of the temperature. So we can cancel out dE1 and dE2. So this will lead us to phi 1 by phi 2 is equal to root of K1 by K2. So let us take this as equation 2. So we have two equations here. The first equation being K1 by K2 is equal to 1 by 3.118, because here it is K2 by K1, which is 3.118. So K1 by K2 will be 1 by 3.118, and also we have phi 1 by phi 2 is equal to root of K1 by K2. Also we have phi 1 as 0.5. So substituting all these into this equation 2, we'll get 0.5 by phi 2 is equal to root of 1 by 3.118, because phi 1 is 0.5 and K1 by K2 is 1 by 3.118. And if we solve this, we'll get phi 2 as 0.885. So this is our Thiele modulus at 470 Kelvin. Now using this, we can find the internal effectiveness factor at 470 Kelvin. So our internal effectiveness factor eta will be equal to tan h phi by phi, and that is basically tan h 0.885 by 0.885, and this will be approximately equal to 0.885. So rounding off this to two decimal places, this will be approximately 0.89. So our internal effectiveness factor up to two decimal places will be 0.89. Okay, so basically what we did here is we just took all the data that they have given. So in this question, they have not given us our reaction rate constants. Instead, what they have given us is the universal gas constant R and the activation energy E. And they have also given us the data that the effective diffusivity can be independent of the temperature, and the external mass transfer resistance can be neglected. So based on all these assumptions, what will be the internal effectiveness factor at 470 Kelvin? And for that, first we needed to find the reaction rate constants ratio, or basically K1 by K2. And to find that K1 by K2, we applied Arrhenius equation, and we found out that K1 by K2 is basically 1 by 3.118. And then we moved on to the concept of Thiele modulus. And basically what we did is we took the ratio of Thiele modulus at 450 Kelvin and 470 Kelvin. And because of the the diffusivity being independent of the temperature, it will get cancelled out. The length is also constant, so L1 and L2 will also get cancelled out. And finally we will get the ratio of Thiele modulus phi1 by phi2 as root of K1 by K2. Also, they have given us the value of phi1 as 0.5, and we also have the value of K1 by K2 as 1 by 3.118. So just substitute all these values in the equation 2, and we'll get the Thiele modulus phi2 at 470 Kelvin, which will come to approximately 0.885. And using this, we can use this Thiele modulus value to find the internal effectiveness factor eta by using the formula eta is equal to tan h phi by phi, and tan h 0.885 by 0.885 will be approximately 0.885. And this will after rounding off to two decimal places, this will be approximately 0.89. So that is the internal effectiveness factor for this scenario. So is this clear so far? Okay. So yeah, we'll stop here for now. So basically, this is all the major topics that are there in CRE. So just to recap all the different topics that we studied in this CRE course, basically we started by looking into reaction kinetics. Then we went on to ideal reactors. And then we moved into multiple reaction systems, and we saw how we can apply the various concepts in the reaction kinetics and multiple reactions in the design equation for ideal reactors. And then we started with non-ideal reactors. Also for multiple reactions, we also looked briefly into the multiple reactor systems. Then we jumped into non-ideal reactors, saw what are all the various non-idealities and the E curve and the F curve and so on. And then we directly jumped into catalysis, and we have been looking in catalysis for the last few classes. So, and here we are right now. So basically, these are the major portions that we covered during our last few classes or last few months of CRE classes. I hope these classes have been useful to you. Of course, we didn't go into much detail with regards to, for example, derivations and so on. We didn't look into the derivations and so on because of the time constraints, but we try to solve various kinds of problems from previous year gate questions using these concepts, and hopefully you were able to take away something from these classes. So yeah, that's all for chemical reaction engineering, and we'll be stopping chemical reaction engineering by today. So next class from next Monday, we'll be starting mechanical operations. So more details on mechanical operations and questions we'll discuss during the next class. So yeah, that's about it for chemical reaction engineering. So any doubt with regards to chemical reaction engineering from any portion or any part of the syllabus, feel free to drop a mail or ask a question during the class, and I'll try my best to help you out. So is this fine, Riaz? Okay. So fine then. We'll stop here for now, and I'll see you next Monday.